This is going to be a quick video that talks about how to find the work done on a rotating system. So just imagine a simple scenario. We have an object or a disk that can rotate about a pivot point, and there's a string wrapped around it, and then you just pull that string with some constant force. And let's say you pull that string some displacement, delta x, and it causes this thing to go through some angular displacement, delta theta. Well, to find the work done on any system, you just take the external force the system feels times the displacement of the system. So with a rotating system, we can get that displacement if we know the radius of the rotating system and we know its angular displacement. It's just given by this equation in our AP Physics 1 equation sheet. Displacement is equal to the radius times the angular displacement. So let's just use this and plug it back into our work equation. So the displacement of the system for something that's rotating is just r times angular displacement. So the work is just the force times r times angular displacement. If we group the r and the f together and multiply that by the angular displacement, what's r times f? An external force applied to a system multiplied by the distance that force is applied from a pivot point. That's just the torque exerted on that system. So to find the work done on a rotating system, how many joules of energy are either added or taken away from a rotating system, just by taking the external applied torque times the angular displacement. And as long as the torque is constant, it's just the constant torque times the angular displacement. We can also find the work graphically just by looking at a torque versus angular displacement graph. Remember, the area of any graph is going to be the y-axis variable times the x-axis variable. So the area of a torque versus angular displacement graph is torque multiplied by angular displacement, which is the work being done. So if we have some torque that's applied over some amount of angular displacement, it's just the torque times the angular displacement, the height times the width. Well, this technique is especially useful when the torque is not constant, if the value of the external torque the system feels is changing, like this second graph. So the area will also represent the work done on the rotating system. So it's just 1/2 base times height. It's the area of a triangle. So in this case, it's the work done is 1/2 times the height, which is the initial torque applied, times the angular displacement. So the two ways you have to determine the work done on a rotating system is one using an equation. It's just torque times angular displacement as long as it's constant. And if it's not, you have to look at a torque versus angular displacement graph, and the area will be the work done. So here's one quick question we can now answer knowing this. A chain attached to the bicycle wheel shown in the figure exerts a clockwise torque of constant magnitude on the wheel. A brake pad, which is a distance RB from the wheel's axle, exerts a force of constant magnitude FB directed to the left. And we're just asked to find what is the net work done on the wheel as it rotates through an angular displacement theta. Well, if we're trying to find the net work done on the wheel, we have to add up anything that could do work on the wheel. The chain is doing some amount of work, and the brake pad is doing some amount of work. So we just have to find expressions for each of those things and add them up. So let's just quickly put things in context. The problem statement says the chain is exerting a clockwise torque of constant magnitude. So it's rotating the wheel in the clockwise direction through some angular displacement theta. And the brake pad, while this is happening, is applying a force to the left, because at the top here, the wheel is rotating to the right, so the brake pad will be pushing back to the left. So the brake is exerting a torque in the opposite direction. So that means we have to find an expression for the positive work done by the torque minus the amount of work done by the brake. And the work done on any rotating system is just the torque applied times the angular displacement. So for the chain, it's the torque applied by the chain times the given angular displacement, which is just theta. We need to subtract the amount of work done by the brake, which is the torque applied by the brake times the angular displacement of the wheel. So let's just factor out a theta. And so we get the torque caused by the chain minus the torque caused by the brake times theta. And notice all of our answer choices, they've got torque plus or minus something. Apparently it's going to be minus something. And now we just have to substitute in for the torque caused by the brake, which is just the force the brake is applying times the distance it's applying that force from the pivot point. The force is F sub B. The distance is R sub B. So we just expand that into FB times RB. I hope this helps you think through finding the work done on any rotating system, whether the torque is constant or it's changing.